Hi everyone. My name is Miguel. I'm finishing my PhD in the mathematics department, and I'm here to tell you about the work that I've been doing along with Justin over there, Edgar over there, and David over there, about peeling and generalized harmonic gauge. So let's start with the concept of peeling. So requiring that null infinity is smooth, it implies a certain decay of the components of the file tensor. Here, these capital psi they just denote certain components of the file tensor, and they're according to Roger Penrose, to the work that Roger Penrose did on this many years ago. These components are supposed to fall off, to have a certain decay that is increasing as you decrease this n that denominates the specific component you're talking about. There's been a lot of work on this by a lot of people, and it seems that in the last few years that there have been a lot of indications that many spacetimes of interest actually don't fulfill this condition. Because they, basically because certain components of the file tensor were found not to have this particular decay, and this is sort of the area that we want to give a contribution in, and which I'm going to try and explain as best as I can. So we started by developing a formalism in which to write the Einstein field equations, and after writing the Einstein field equations in the specific formalism that we need, and that gives us the most, the biggest number of advantages, let's say, in the method that I will explain a little bit later. Basically, what we want to do is to find the asymptotics of these components of the file tensor. We want to compute them directly from the metric written in the variables that we choose. So first of all, I'm going to explain how the formalism is built, and then I will explain why it's useful. So we begin by defining these outgoing and incoming null vector fields, psi and psi bar, in terms of the vector basis. They can be written as d by dt plus c plus minus r d by dr. These c plus minus r are scalar functions that are fixed by the requirements that these vector fields are null. From those vector fields, we can define covector fields, sigma and sigma bar, and we multiply them with this factor here that is fixed by the requirement that the r components of the sigma and sigma bar are plus and minus 1 respectively. Of course, there's a lot of freedom in this, right? These are just choices in the way we build this, and we've even tried different formalisms built in different ways, and this is the one that we found gives us the most, makes the maths easiest, let's say, in the type of differential operators that we're going to be using. So using these null vector fields, we can build the metric with indices upstairs, and multiplying it with a certain factor, then basically we define this g slash that's basically the inverse metric minus this, and the factor we use it, or we have freedom in choosing the factor as well, and that factor was chosen so that g slash is orthogonal to these to the null covector fields. Yeah, that also makes things significantly simpler. We can also write the metric with indices downstairs in terms of the null covectors, just like that. And then there's also some freedom in the way we split what we call the angular metric, which is g slash. So first of all, we take out of the metric this conformal factor. Basically, it amounts to taking out of g slash the 1 over r squared, with r being suitably defined radial coordinates, and e to the epsilon being the determinant of G slash over the determinant of the flat G slash squared. We can also split this conformal metric Q inverse in two more variables, which are going to be H and H cross. The way we built this is not so important for this discussion. So I'm going to just leave it at that and say the most important thing which is that we end up with 10 independent variables. That's var phi, C plus minus R that are defined in the null vector fields, C plus minus A in the covector fields, epsilon from there that comes from the determinant of G slash, H plus and H cross from the conformal angular metric. Now comes a system which is a toy model. It's usually used as a toy model for the Einstein field equations. Many of you have probably heard of this, since some people here are working on the system. So how do we define the system? First of all, we define a Cartesian harmonic Cartesian coordinate system. And then we define a covariant derivative that is adapted to this coordinate system, meaning that it reduces to partial derivatives in the specific coordinate system. And then from that, we define a wave operator. That's basically two covariant derivatives contracted with the inverse metric. So from that, the simplest equation that we can build is one that is wave operator hitting this field G and then homogeneous on the right hand side. Here G stands for good, B for bad, U for ugly. Goods and the name good and the name bad come from the way these functions behave asymptotically. The name ugly comes from the movie. Actually the uglies behave even better than the goods, asymptotically close to null infinity. I'll explain that in more detail a little bit later. What matters here is that this system is generally used because it's known to mimic the Einstein field equations asymptotically close to null infinity. So we want to study this system in detail, and we want to generalize it enough so that we can take conclusions from that actually apply to the Einstein field equations. In a paper that we published, I think early last year, this one here, we studied the system in detail. The leading order asymptotics of these equations was already known before. So what we did was to extend that, but basically we found that there's an induction proof to be done. Basically, expanding these wave operators, you can work out an induction proof that tells you the functional form, or basically how the next order down close to null infinity in the expansion in powers of 1 over r behaves as related to the previous one, right? So it gives you a recursion relation in the end that tells you that, for example, a good field behaves like this. So at each order, it's basically a function that doesn't vary along psi. Remember that psi are the outgoing null vectors. So as you go out to null infinity, these functions don't vary in that direction over powers of 1 over r, or over powers of r. The bads behave similarly, except that the numerator is built like this. Basically, there's a function just like the good one that doesn't vary along integral curves of psi, and then a function that also doesn't vary along integral curves of psi times a factor of log r. So you can see why these are called bads and these are called goods. It's that basically that's a leading order. These guys fall off like close to null infinity. They fall off like log r over r, and these guys fall off a little bit faster, which is just like 1 over r. The uglies, they behave to leading order. They behave more or less as goods, or to leading order they can even be said that they're goods, in the sense that this function here it doesn't vary along integral curves of psi, but also it has the added advantage that it doesn't vary along integral curves of psi bar. So it's basically an angular function. It depends on theta and phi. Yeah, that's it. There's an important detail here, which is that so to leading order, this ugly behaves really well in the sense that it generates no logarithms, but from second order on, so at second order, these functions, so functions that satisfy an equation like this, start generating logs. So basically, they behave more or less as a good in the leading order, and then from sub-leading order on, they behave as bad. So basically, logarithms in a system like this, which is the simplest possible, with a flat metric here on this side, you have logarithms being generated here at first order and here at second order. That'll be important a bit later. So what we did was to generalize the system as, in strategic ways. The first obvious generalization was to not use a flat metric, but a general asymptotically flat metric on the left-hand side. So obviously that creates a significantly more complex differential operator on the left-hand side. And then we went further than that, and we allowed each of the equations to have these ends here. And these ends are what we call stratified null forms. Stratified null forms are basically any terms that, but they basically have two restrictions. They cannot have derivatives higher than first derivatives, and also they cannot contribute to order 1 over r squared. They can only contribute to orders beyond that. So what this means in a system of equations built like this is that these terms are not, by definition, contributing to the principal part in the PDE sense, and they're also not contributing to leading order. So it seems a little too convenient that that we choose that definition to be the case for the stuff that we allow these equations to have on the right hand side. But in fact, it turns out that in the formalism that I just explained to you how it works, which is highly non-unique, you can actually write the Einstein field equations in a certain gauge as just a set of equations of this type. So before we head out to general relativity, I want to just tell you how these things, how this generalization basically affects the behavior, the asymptotic behavior near null infinity of these functions, these fields. So basically, to leading order, they're exactly the same in the sense that the good behaves as good to leading order. There's no logs. It's just a function that doesn't vary when you go out to null infinity over R. Here it's B1 as defined before, so it contains a log. So basically, the leading order falls off only like log R over R, and this is an angular function over R. Now, what's different is what's beyond leading order in the sense that now basically these stratified null forms, they could even be coupled, right? So there could be any number of derivatives of bads or uglies here, and so on and so forth. And what that means is that logarithms that are generated here and here, so here at leading order and here at second order, they could be inherited by any equation at any point, at any power, basically. So because we didn't specify any kind of structure on these terms. So basically, in the end, what we get here from second order on is what can be called a polyhomogeneous expansion, basically an expansion in powers of 1 over r, in which the numerator can have basically any power of logarithm. Now, this any power of logarithm is really the what matters here, and that's determined by this big N here, basically, which we don't know until we specify more structure on these equations, and that's what considering GR will give us. So basically, yeah, that's it. So let's move on to GR. First, we have to define a few quantities. This is what we call the reduced Ricci tensor, and it's defined as the Ricci tensor minus covariant derivative symmetrized hitting the constraints set. Constraints are defined as contracted Christoffel. So basically, the two lower indices in the Christoffel tensor that takes you from one of the the Cartesian covariant derivative that I defined above to another set of covariant derivative, which is called the shell covariant derivative, which is adapted to this coordinate system, which can be thought of as a normal spherical polar coordinate system, plus the gauge source functions, which encode basically the gauge choice, plus constraint addition. So basically, we want here to in the end we want to treat this as an initial value problem. So we don't want and we don't want the constraints to be set to 0 immediately. But we want to be able to add the constraints to the evolution equations freely. So that's what's encoded here in this WAB. So now comes the freedom in the that GR gives us. There's the choice of gauge and also the choice of constraint addition. As I said, choice of gauge is encoded here in these gauge source functions. And we decided to start with the most obvious choice, which would be Cartesian harmonic gauge, which is basically choosing gauge source functions to be that Christoffel tensor that I was that I just introduced, contracted with the spacetime metric, and choosing this choice of gauge basically amounts to choosing that the coordinates that we're using are harmonic. Constraint addition. We have 4 constraints to add freely to each of the evolution equations, and it turns out that to leading order, each of these constraints is basically a time derivative of one of the metric functions. And as I showed you before, that's more or less what the uglies look like on the right-hand side to leading order, right? So as it turns out, you can actually turn 4 of the field equations into uglies just by constraint addition. So doing that and choosing this gauge, what you get is something like this. I wrote here the generalized good, bad, ugly systems just for comparison. And what you get here is what you have here on the left-hand side is basically the wave operator hitting each of the metric variables that I introduced. There's quite a long calculation to be done, basically to write the Einstein field equations as wave equations for these variables. But once that's done, if you look at the leading order contributions, basically you can write all of the Einstein field equations as this system, basically. So if you look at this carefully and you compare this to that, you see that phi, for example, is clearly a good. Remember that like all of the complexity of the nonlinearities of the Einstein field equations are here swept under the rug in this n, right? But what we know about this n is very specifically that they don't contribute to leading order, and also that they don't have second derivatives. Right? So look at C plus R. It's clearly an ugly as well. C minus R is a bad. The structure of this is slightly different from that, but it amounts to the same asymptotically, and so on. So basically, what we get here with this particular choice of gauge and this particular choice of constraint addition is that the Einstein field equations turn into 3 goods, 1 bad, and 6 uglies. And this immediately gives a lot of information on how the metric behaves to leading order and also to sub-leading order. If we get to know the amount of the power of logs, as I said, that's encoded in that big N that I showed you in the polyhomogeneous expansions. So yeah, basically that's the next step that we need to do. Basically, since we already know the character of each of the fields of each of the metric fields in this particular setting, then we know how they behave close to null infinity, and we can plug that polyhomogeneous expansion straight into the Einstein field equations and see what we get. So through computer algebra, you can see how they basically the amount of, or the power of logs that they're allowed to have to the first few orders. Of course, the complexity of this and the computational time increases significantly as you go beyond first order. But fortunately, to get to the result that we need, you don't need to go very far. So doing that, basically, we built the metric, and then from the metric, we built the components of the Weil tensor, and we found out that the psi4 peels. Basically, it has the expected fall off. Psi3 also peels, it has the expected fall off, but psi2, instead of falling off like 1 over r cubes, it falls off only like log r over r cubes. So it falls off slower than it would be expected for a smooth null infinity. So peeling is violated. And this is not super surprising in the sense if you consider what's been done in the literature in recent years. What we found more surprising is that if you explore a little bit the interaction between the choice of gauge and also the constraint addition, you can very carefully pick the two in order to turn these equations into a very specific set of equations that will basically recover peeling. So the way to do that is to consider gauge source functions that are the same as we chose before to leading order, but then you add a second order correction, which will leave free until we plug them in the equations and see what's good for us. And then the constraint addition, as it turns out, it pays off to generalize even more a little bit the notion of an ugly equation that we had. Basically, this equation has this natural number p here, which was usually set to 1 before. But if you leave it as just a natural number, as it turns out, that log that used to be created at second order in the uglies, it basically gets pushed more orders down as you increase p. So if p equals 1, your first ugly log, let's say, is going to be created at second order. If p equals 2, it's going to be created at third order, and so on. So the first log appears at order p plus 1. That's what's important here. So if somehow we could choose the gauge and the constraint addition so that we would only have uglies of this very special kind and goods, not only would we not have the bad logs getting generated at first order, we could also basically control the order at which the first ugly log appears, right? So we could have the freedom to prevent the appearance of logs at, until arbitrarily high order. So that's what we want to do. That's what we want to do here. If we have this, consider this hypothetical system in which you only have goods and uglies of this very special kind, then basically, whereas before you had this is basically what I showed you before, right? So they're goods, bads, and uglies to leading order, and then they have any number of logs from second order on. So imposing no more structure on the right-hand side, you're basically preventing the existence of logs up to order p plus 1, right? So you have the same behavior to leading order, and then up to order p, you have still the same behavior in the goods and still the same behavior in the uglies, basically pushing the logs further down. That's what these complicated expansions are meant to explain. So yeah, as it turns out, you can do that with basically with the 4 constraints and the 4 gauge source functions. You can turn a total of 8 out of 10 equations into uglies of this very special kind, and the 2 remaining ones are the H plus and H cross, which are naturally goods. They were goods before, and they're goods now. So in the end, what you had as a asymptotically very complicated system, you can turn into a very neat system of equations that are basically, you see, 8 uglies plus 2 goods. Yeah, once again, this only looks nice and clean because all of the complexities are swept under the rug here in these stratified null forms, right? This is just the asymptotic part and the principal part. So just a note on initial data. So basically what I mean here, let me see. Yeah, basically what happens here, if you take these fields, you plug them in the metric and you compute the file tensor, is basically that you can prevent the logs from appearing in all the orders that could possibly contribute to the leading order of the file tensor, right? So you know, say you're free to choose P, right? So why not choose a 10? Choose it to be 10, then it already prevents any logs from appearing in the leading order of the file tensor. And so by choosing carefully the gauge and the constraint addition, basically you can recover peeling. That's the point of this work, which should come out very soon. Yeah, just a note on initial data. Basically, just for completeness, I wanted to tell you how we the restrictions that we have on initial data. We choose if S is a Cauchy surface defined by a constant value of the coordinates t, then these are the restrictions that we have. So basically, at spatial infinity on this Cauchy surface S, the fields themselves, so basically the metric fields, have to fall off like 1/r, and the time derivatives of these fields have to fall off at least like 1/r squared. How am I doing on time?
You've still got 15 minutes.
Yeah, cool. So yeah, moving on from peeling, we decided to use this. So that, you know, there was a lot of artillery, heavy artillery involved in all of this result, and we figured that it would be interesting to try and use this for something other than peeling. Basically, what we did was to try and contribute and give some contribution to an open problem in numerical relativity, which is the inclusion of null infinity in the computational domain. One of the problems in this, in some of the formulations to do this, is that these funky logarithms tend to appear at null infinity, making the numerical evolutions very problematic, because if you rescale the variables that you have close to null infinity to get rid of the powers of 1/r, then you're going to end up with integrating variables that diverge at null infinity. Certainly you cannot have that, and so we thought that this could be a way to basically a way that we could explore basically to solve this problem as well. So this is another thing that we're working on right now, and it's almost done. So basically what we did was to go through the same process as in the peeling results, basically going through a regularization of the Einstein field equations by choosing carefully the gauge and the constraint addition, so that we can only have uglies and goods, and we can prevent the existence of logs up to order p. So then we write that we are able to write down all of the Einstein field equations as basically this. These are stratified null forms, and this is like an alternative wave operator, which is the normal wave operator that we had before, plus the stuff that was on the right hand side that contributes to leading order, that determines whether the function is a good or an ugly. And this p here determines basically that. So basically, if p is 0, then the function is a good. If p is another p, then the function is an ugly. So basically, it's interesting to write the equations in this way, because here you have all of the principal part and all of the leading order contributions on the left hand side, and all of the stuff that doesn't matter to either on the right hand side. So if you do that, and then you do a first order reduction, which is basically to treat the derivatives, the various derivatives of the various metric variables as variables in their own right, then you can write a significantly larger set of equations that are first order, right? So the second derivatives that you had are now first derivatives of the reduction variables that you defined, right? and you treat these variables basically as variables in their own rights, which you then want to evolve. And the next step is compactification. You choose a specific coordinate system that basically what it does is basically bring null infinity to a finite coordinates value. So basically, whereas as r radial coordinate goes to infinity, then this specific compactified r goes to a specific a finite value, let's say. So if you do that, so very recently we were able to do all of this and to write the Einstein field equations as this set of equations, which is once again it's a system of first order equations which are regular in the sense that they do not contain logs up to order p, and p here is still it's actually q here. It's a notation error, but basically the order at which logs are allowed to first appear is determined by this q here. So it's still free. And yeah, these are regular equations. The system is symmetric hyperbolic. It's a system of 55 equations for 55 variables because all of the derivatives are now variables in their own right. Yes, this is a result that we expect to be important then in basically applying to numerical evolutions, which we haven't done yet, but we will hopefully in the future. Thanks very much for your attention.
Thanks very much for the great talk. Do we have questions?
I have a question. When you recovered filling, so you had like the first gauge choice and you didn't have it, you recovered it. And sort of the magic part was in this new choice of gauge, you know, like the second gauge you chose, which in the end, I don't know this, but I don't know, my question is like, yeah. But the scalars are scalars, right? So in a sense, the differences in the coordinates you're using, or to my understanding, right? Like gauge is related to choice of coordinates. So what does the magic? I don't know how to ask it. Like you know, in some coordinates, bias would behave as log over r, and in these new coordinates included. Like, can you elaborate a bit why that happens, or what is your choice of using f, like to cancel those terms, or I don't know.
So basically, I think if I understand correctly, you're asking why does something that amounts to a change of coordinates change scalars, right?
Yeah, exactly.
Yeah, that's a good question. I'm not sure I know how to answer that.
I mean, there are different coordinates, of course, but still, you know, they're scalars, right?
Yeah, that's true. It would be interesting to discuss that later, but I don't have an answer for you.
I can take a stab at it, but Justin did the right calculation for that. Well, actually, you did it afterwards, but I forgot. So the thing is that even if you've got a space-time where everything is like legit smooth, right? You could still choose coordinates which the metric doesn't look smooth. Right? And so the calculation which exists somewhere in one of these two algorithms is that if you start from the side where keying is true, right, in this formalism, and then you change coordinates to undo his magic fix, then again keying gets violated. Right, and it's essentially like there's something going on in the choice of radial coordinates that somehow it gets. The two radial coordinates across those two gauges don't agree with each other. They're different, and that difference means that a log of it is somehow expansion or not.
That kind of suggests that these logs are coordinate logs, right? The logs that you see go infinity.
More generally here, like you either have them or not, because the constraint, like we don't assume that the constraints are satisfied in the analysis. So think is that, okay, if I do the analysis and then I see, that like, what's the best possible thing I can do when the constraints are I don't assume that the constraints are satisfied. That's the result that you would have if the constraints were satisfied.
Yeah.
Do we have other questions? No, well, I would have one if that's okay. So it's a very naive one. So you showed that the psi, like I think it was the previous slide, psi 4, psi 3, they're still as expected. Psi 2 is not. What about psi 1 and psi 0? Are they also changed? If you know.
That's a question we did not answer. As I said, the basically computing going one order further makes things much more complex, right? So it was actually a relief that this log appeared so soon, because if psi 2 had peeled, then it would be quite complicated to go down to psi 1. So this this was enough to prove the result that we wanted, which is that peeling is not true, and so we didn't go further. I suppose it is possible, but significantly more complex.
Thanks. Any other questions?
Do you have any particular number of P, or you can make it arbitrary?
Well, P, we're just putting basically P is just something that we're including in our choice of gauge and our choice of constraint addition. So it's we're completely free to choose. Yeah, it can be chosen. Yeah, and it turns out that to recover peeling, so to guarantee that peeling is true, 7 is enough. P equals 7 is enough. Yeah.
But we don't want 7 in the code. In the code, we want 1.
Yeah, so it's different problems, right? I mean, you can show that there's there are coordinates and constraints and choices of constraint addition where peeling is not violated, and then when you want to implement something, you don't need logs to be prevented up until arbitrary order, right? You can deal with logs at second or third.
But if the logs would appear only in equal at one term, then why do you need 7? Like seems to be now.
Well, peeling, you see, the reason is that, if I can explain without showing too much maths, where's peeling? There. So, peeling goes up to order 5, right? And then you have certain equations or certain variables in the metric that because they come with the r squared from the angular metric. You still have 2 orders that you have to compensate, let's say, and those 2 orders will give you the p equals 7. Basically, you need to basically what you need is that p is big enough so that no logs appear to any of those orders. Right?
Can you try to get more maybe on the relationship between your peeling result and what's in the literature?
No, but I can say why. So basically, what's in the literature is I think most of it is done using the conformal Einstein field equations, and not only the formalism but also the choice of initial data. It's not clear. So the methods are so different and the formalisms are so different that it's not clear how they relate to each other, right? So we could go any number of ways to do that, but it would be probably a huge workload in itself just to compare the 2 methods. Of course, it's valid and it should be done at some point, but it's not something that you can just eyeball and tell what the differences are, because the methods are so different. So yeah, when we talk about this result, it seems to kind of contradict let's say what's believed to be true these days because of all of the indications that come from the conformal field equation, conformal Einstein field equations. So people are usually eager to compare, but it's not easy at the moment to do that.
Any more questions? So if not, let's thank our speaker.
If you enjoyed the video, like and subscribe.